So the last step, the last learning standard for our semester, is to investigate the properties of continuous functions. And particularly, we want to look at the various ways of characterizing what it means for a function to be continuous. And so when we first talked about continuity last Friday, we had kind of this originalist definition, the limit definition, what you might say, limit definition of derivative, or sorry, limit definition of continuous. Let me get my head out of the calculus classroom here for a minute. Continuous. Limit definition for continuous, a continuous function at x naught. Remember that this limit definition says that a function is continuous at x naught if the limit of the function as x approaches x naught agrees with the value of the function at x naught. So this was the limit definition. And in order to employ this limit definition, what we need is the definition of a limit, the definition we were just talking about, right? If we wanted to actually verify that this holds for a particular function, we would need to establish that this limit over here exists and is equal to f of x naught for whatever x naught that we pick. But the other part of this learning standard is to understand the other ways in which we can think about continuity. And there are two others that I want to bring to the forefront here. One of them is called the sequence definition. And so, as you might expect, here we're going to be using the tools that we developed in Unit 2 of our course, continuous at x naught. And then the other, so before I tell you what that one is, let me tell you what the third of our characterizations is called. It's going to be called the open set definition. I call it the open set definition of continuous. Your authors of your book call it, I think, the mapping definition. Let me call it the open set definition of continuous at a point x naught. Okay. So each of these relates to saying that a function is continuous at a specific point. We could broaden them out to say what it means for a function to be continuous on an entire set or continuous for all real numbers. But for now, we just want kind of what analysts would call a local definition of continuity. What does it mean to be continuous at a single point? Let's talk about the sequence definition of continuity. So here I have the graph of a function that's actually pretty nasty. It's a sine of 1 over x. And so you can see a lot of weird stuff is going on with this function. What the sequence definition of continuity says, if we investigate the point x equals 0 for this particular function, the sequence definition says that our function is continuous if every sequence of x values that approaches 0 has the same sequence, the same limit of the sequence of its y values. Okay. So let me get that written down on paper, and then we'll talk about what this visual is doing, because this relates to one of your homework problems. So f is continuous at x naught if and only if for all sequences, let's call them xn's, of x values, such that the xn's converge to x naught, we have the sequence of the y values of those points, f of xn, converges to f of x naught. Or at least, at minimum, that they all converge to the same limit value, right? So in other words, a sequence of x values will, if any sequence of x values converges to x naught, then its corresponding sequence of y values converges to f of x naught. So in this picture, we're kind of trying to show that the sine of 1 over x is in fact not continuous at x equals 0, doing so by finding two different sequences of x values that converge to 0. So here's one sequence of x values converging to 0. Here's another sequence of x values converging to 0. But the y values that are taken along that sequence are different for these two different sequences. So here's an example of a function which is not continuous at 0 because two different sequences, both of which converge to 0, have y values that do not converge to the same point. So for one of these sequences, the y values are converging to 1. For the other, the y values are converging to -1. And on the homework problem, I'm actually going to ask you to find specific formulas for these sequences that indicate why this happens. So just to get this on paper again, sequence definition, just to summarize it, is that if xn converges to x naught, then f of xn converges to f of x naught. Converges to f of x naught. I'm being very sparing on my words here on the screen, but hopefully it's clear what this means. Maybe I'll put the quantifier here for all. Okay. For all sequences xn that converge to x naught, the values of f of xn converge to the value f of x naught. So let's also talk about how to characterize continuous functions by their behavior with open sets. So I call this the open set definition, or your authors of your book call it the mapping definition of continuity. So here's a function, f of x equals the absolute value of x. I've got its graph listed up here, or shown up here with the v, right, in dotted lines. And the idea behind the open set definition is that a function is continuous at a point x naught if whenever f of x naught is an interior point of a set, then x naught is an interior point of its pre-image. So let me write that down more explicitly here. It's continuous at x naught if and only if whenever f of x naught is an interior point of some set. So I'm just going to call the set A. So whenever f of x naught is an interior point of a set A, we have that x naught is an interior point of the inverse image of A, f minus 1 of A. So here, this is giving us what mathematicians would call a topological criterion, topological characterization of what it means for a function to be continuous. Because this definition has no specific data about the real numbers or sequences or completeness or any of that stuff. It only has to do with open sets. Right? So as long as we know what an open set is, in other words, as long as we know what it means to be an interior point of a set, right? As long as we know what an interior point is, these are things that we can directly verify. So on this particular graph, supposing that I choose some point which is interior to this open interval from A to B, and let me call this point y. Y is interior to the open interval from A to B. Then if there is a point x such that f of x is equal to y, and in this particular example there are two different points, I'm just going to pick on one of them. So if I go to this point over here, x, and this point here satisfies f of x is equal to y. But what we observe here is that the x that corresponds to this y actually is interior to the inverse image. Let me slide this over here. The inverse image of the set, and here the role of the set is played by the open interval from A to B. So another way of packaging this message is to say that the mapping definition, what the open set definition really says, is that continuous functions satisfy that the inverse image of an open set is open. That's really, after all, what we're proving when we say that the preimage of an interior point is an interior point. The inverse image of an open set is open. That is behavior that we associate with continuous functions. And in the textbook, they actually show that each of these three criteria, if f of x naught is interior to A, then x naught is interior to the inverse image of A. And our text, the authors of our text show that these three characterizations of continuous functions are all equivalent. Okay? That it's not possible for a function to meet one of these definitions without meeting all three of them. One of your exercises on the upcoming homework is to show that we could also replace the word open with closed here and still have an equivalent characterization of continuity. We just pick on open for kind of historical reasons, that really what it means to specify topology for a space, what it means to say when 2 points are close together, for example, really is a specification of open sets. So open sets are kind of the bread and butter of topology. And so closed sets are interesting insofar as they're related to open sets. And there's a specific relationship between open and closed sets that we learned about a couple of weeks ago that you can use to crack the nut on that one. But for the sake of brevity, we just keep this open set definition alongside the sequence definition, alongside the limit definition, and these three are all equivalent one to another. For you on the back side of the page is to prove just one step in that equivalence, and it's the step that if we have a function that's continuous at all points of E, and U is any set, then prove that our function satisfies this open set definition of continuity. So I guess what I'm asking you to prove here, to write a proof for, is to show that the limit definition of continuous implies the open set definition of continuous. And so, again, if you're trying to show that that is true, what you mostly need to think about is the definition of interior point that we learned about a week and a half ago or so, and how that definition of interior point, remember it has this connotation of the points have some breathing room, right? And the amount of breathing room that those points have is probably related in some way to the epsilons and the deltas that make up the limit definition of continuity. So the tricky part, I think, in that proof is to make that connection between the C's that appear in the definition of interior point and the epsilons and the deltas that show up in the definition of limit continuity.